Got it? It's going? Okay. I'll begin with a word of prayer. I'll try anyway. Ahem. Dear Father, we thank you for this day. I thank you for the students. Just pray you just bless this lecture and this class, Lord. In your name I pray. Amen. Okay, so last time I tried to give you some indication of why we care about a group. Well, maybe not we, but why mathematicians cared about what a group is. Why this subject has been studied intensely for about 200 years or so. And then I, at the very end of lecture, introduced the term ring, right? A ring is something that has an addition and a multiplication, which basically the addition and multiplication interact like you're used to. There's a distributive law. The multiplication is not generally commutative, but if it is commutative, we say it's a commutative ring. We also assume that the ring has something in it that's like the number 1. The one thing I failed to say last class, I think in any way, is that in a ring, if we have a ring where every non-zero element has a multiplicative inverse, then that sort of ring is called a field, right? So fields are often what you've worked with: real numbers, complex numbers, rational numbers. These are fields, right? So anyway, we'll get back to rings eventually. I just wanted to mention that terminology briefly. And just to say a comment, which is, have I covered everything? Did I say everything in class that's written in lecture 1? No, of course not, right? So I do expect that you read that, think about it for yourself. If something in there doesn't make sense, you should ask me about it, right? So with that, I'm going on to lecture 2, which is on examples of groups. So I would just remind you that we already have four examples from last lecture. Vector space with addition. If we take a field and we remove 0 from it, right, then that's a group by the multiplication of the field. We said that the set of invertible matrices with real entries forms a group with respect to matrix multiplication. And finally, the set of all bijections, which we called the permutation group, is a group. All right. So today we're going to add to that list of examples. All right. And as we're adding to that list of examples, I'm going to discuss a new concept. Well, I guess I defined this last time, but we'll talk more about it today. Order of a group. Right? Order of a group. We denote by G like that. So this is equal to the cardinality of G. Now I'm thinking of G being a group, the cardinality. So of course, if it's a finite group, then the cardinality is a number, right? And if it's an infinite group, the cardinality is, well, it is what it is, right? There are different kinds of infinities, right? Cardinality of the natural numbers versus the cardinality of the real numbers. These are different. So, but anyway, we don't really do too much with transfinite arithmetic in here, so I wouldn't sweat it. Let's get an example. I mentioned this example last time, but actually this is a good example to have written down. S3, the permutations on 3 elements. In cycle notation, we've got the identity. We've got the transpositions, 1, 2, 1, 3, 2, 3, right? And we also have the 3 cycles, 1, 2, 3, and 3, 2, 1, right? So this is permutations, S3. What's the order of this group? You're like, it's 3. No, sorry, still a stupid joke. 3 factorial, which is, by the way, 6. But the 6 is just from counting, right? 1, 2, 3, 4, 5, 6. 6 elements, order 6. We also would like to talk about the order of an element. All right. So I'll put that in here too. Going a little bit out of order from the notes, but that's okay. The order of G in G is the smallest n in the natural numbers. Our natural numbers start at 1, all right? So it's the smallest n for which g to the n equals to e, where e is, of course, the identity in the group, right? That's the order, excuse me, of an element. In additive notation, it's the smallest n for which n times g is equal to 0. Where remember that n times g is just notation for repeated addition of g to itself, g plus g plus g plus g plus g plus g, right? What does g to the n mean for the permutation group? If I take a permutation sigma, what does sigma to the n mean? What would sigma to the n be means? What does this mean for sigma in the permutation? What is that? What's the meaning of sigma to the n here in that context? How about sigma squared? What's that mean? It means sigma composed with sigma, right? That's function composition. So sigma to the n means n-fold compositions of sigma with itself. All right? So when I talk about g to the n or n times g, you have to understand that in the abstract sense, right? It's a repeated operation of the group, whatever that operation has to be. All right, so now that we have this definition, the order of an element, you can tell me what's the, let's see, like 1, 2. What's 1, 2 times 1, 2? Remember, we learned that that's the identity. So what is that? Is 1, 2 equal to the identity? No. So what's the order of 1, 2? By the way, the order of a group element is also this. So if we write, that's the order of a group element. Now some books will use like little o of g for order of the element, but I tend to use just vertical bars for the order of the element. All right? If in doubt, use words. So this says that the order of the transposition 1, 2 is 2, right? Likewise, what happens if you take 1, 2, 3 and multiply by itself? What's 1, 2, 3 squared? Let's work through it. I'll start with the number 1. Where does it go? Yeah, 1 goes to 2, but then where 2 go? 3. So 1 goes to 3 in this product of cycles. Then where's 3 go? 3, and the first one goes to 1, then 1 goes to 2, so this is this, right? Which, by the way, could also be written as 3, 2, 1. So in fact, the next to last permutation here, 1, 2, 3 squared, is actually the last one. Anyway, the larger point here, of course, is that the square of the permutation 1, 2, 3 is not the identity, right? But you can calculate that the cube is equal to the identity. So in fact, the order of 1, 2, 3 as an element is 3. So just to go through the list here, the order of the identity in S3 is 1. The order of the 2 cycles is 2. These transpositions each have order 2. And the order of the 2, 3 cycles is both 3. But this is part of a larger story, right? I proved in the prequel on permutations that a K cycle, right, has order what? Order K, right? What if we had the another example of cycle order, another example while we're at it. What if I was working in S10 with sigma equal to 1, 2, 3, 4, 5, and beta equal to 3, 4, 7, 8. What's the order of sigma beta? How would you figure that out? What did we learn? Yeah, it's the least common multiple of the lengths of them is what I was hoping to fish you guys into. Why is that wrong?
They're not disjoint.
Right, they're not disjoint. It's a trap. So what we first have to do is to find the disjoint cycle decomposition of sigma beta. 1, 2, 3, 4. It's like Dr. Cook is not being friendly today. Let's see here. That's right. It's entrapment. Let's see here. So let's work it out. 1 goes to where? Nowhere. It goes to 2. Where's 2 go? Nowhere. Goes to 3. Where's 3 go? 3 goes to 4. 4 goes to 5. Where's 5 go? 5 goes nowhere. 5 goes to 1. Oh, back. Done. And then what's next? 1, 2, 3, 4. Maybe 4. Start with 4. 4 goes where? 4 goes to 7. 7 to go where? No. 4 goes to 7. 7 going where? 7 goes to 8. 8 going where? No. 8. 8 going where? Well, 8 goes to 3. And 3 goes to 4. Oh, there. Yep, done. So anyway, odds are very high. It would take you longer to do that calculation right now. Am I right? Okay, that's fine. You're still learning. But that is what you get. And so what's the order of sigma beta? It is the least common multiple of 4 and 3, also known as 12. What's the order of S10 as a group? It's equal to 10. I'm sorry, that's my third time telling that joke. I think I'm done. Which is like 10 times 9 times 8 times 7 times 6 times 120 there. Anyway, it's big. It's big. It's big. So, all right, enough about that. Where was my, oh yes. So moving along here. So I hope that gives you a sense of what is the order of an element versus the order of a group, right? The other main example that I want to introduce right now for you is Zn, right? So let's call this groups associated with the ring of, all right, this Zn ring. See, Zn has addition, and it also has multiplication, right? And we defined those. Remember, we said if you take x and you take y, then we take x, y, we take the, multiply the representatives and take the residue class of that, and then the addition, likewise, we proved was well defined. This guy, remember? We had a discussion about this in the, well, it wasn't a discussion, it was more of a monologue. If it was a discussion, that would have meant that you were inside my house at some kind of strange hour, and that would have been a little bit creepy. So, and impressive that you can anticipate I was giving the lecture on that day at that time. I mean, really. So the point is, with Zn, we have these two things to play with, addition and multiplication, all right? There's two different groups you can form. Two groups. And it's important to understand which one you're working with, because one is multiplicative and one is additive. All right? So Zn paired with addition, this is an additive group. All right? And it works on the whole of Zn. Is the sum of two things in there again in there? Yes. Are there negatives? Yes. Is 0 in there? Yes. Does everything have an additive inverse? Absolutely. This isn't a group. Is modular arithmetic associative? It is. That's a group, right? And then something that's a little bit more interesting, UN, all right, which is part of a larger program of notation, which is U of Zn. In other words, it's the units in the ring Zn. So this is a multiplicative group. Let me give you a standalone definition. Un is equal to x in Zn such that the greatest common divisor of x and n is equal to 1. Of course, this is logically equivalent. I'm sorry. To be pedantic here, and because I don't want to beg questions about what is the GCD of a residue class with an integer mean, I'll write it like this. Right? So I'm taking the greatest common divisor of the representative with n. We've defined GCD for integers. I have not defined GCD for modular residue classes. Now the definition at least makes sense. All right. So before I prove to you that that's a group, let me just list a few of these basic examples, all right? So first example, U2. What is in U2? What is in Z2? See guys, this is going to be a subset of Zn. This is going to be a subset of Zn, and it's not the whole thing. I know that for sure. How do I know that for sure? Because 0 does not have a multiplicative inverse. Right, so that's not in there. But anyway, U2 just has 1. In contrast, Z2 has 0 and 1. If you don't mind, this is that place I'm going to not be writing. I'm using this notation, right? Because writing bracket sub 2 and bracket sub 3 and bracket sub 4, and after about the 100th one of those I wrote today, we would all agree it was a dumb thing for me to have done. So let's just let context guide our notation, all right? So U2 is a group with just one element, right? U3, my second example. We got 1 and 2 in there, right? In contrast, Z3 has 0, 1, and 2. Was that sarcastic? Z3 has a 1 up on, oh yes. It's going to get worse. But this is a good time as any for us to take a chance to introduce the so-called Cayley table. So, or operation table if you like. I may have introduced it before. I'm introducing it again. So we can make these little tables that illustrate the operations in the group. 1 times 1 is 1, 2 times 1 is 2, 2. What's 2 times 2? 2 times 2 is 4, which is 1 mod 3, right? And on the other hand, the additive Cayley table for Z3, which of course is a different group. So these are kind of interesting examples in the sense that they're different, but they're related, which means there's definitely an opportunity for confusion here, am I right? That's why I'm doing them both at once, so you can be aware and confronted with the relation, but also be aware of their difference. Because it's important for you to separate these two groups in your mind as we discuss them. When I took abstract algebra, I did it as an independent study. I just read Galilean, and then I took tests. And so I definitely labored under this confusion. I'm like, is Zn additive or is Zn multiplicative? What is going on here? So I'm partly telling you this. You might think, why are you spending so much time on this? This is obvious, but trust me, if you have this confusion lingering, even a little bit in the first test, it will kill you, right? You need to separate this additive versus multiplicative. Be aware of the distinction. All right, 3, U4 versus Z4. So Z4 has, of course, 0, 1, 2, and 3. So the question is, which of these numbers, 0, 1, 2, and 3, are relatively prime to 4? One? And 1 is always in there, okay? And 2 is out, because 2 times 2 is what? It's 4, which is 0, right? So 2 is what's called a zero divisor. Right? Those cannot be in the group of units. Zero divisors are not units, but 3 is in there. So actually, U3 and U4, they have the same size. What happens if we look at the Cayley table for U4? What's 3 times 3? 9, but what's 9? It's 1. See? So you can start to look at this, and they look very much what? They look the same, don't they? That's what we're talking about Friday. What does it mean when two groups look the same? Those kinds of groups are said to be isomorphic, right? Let me jump ahead a little bit. 10. U20. What's U20 look like? What are the numbers relatively prime to 20? 1, 2 is out, 3 is good, 4 es no bueno, because 4 times 5 is 20, which is bad because that's 0, which means neither 4 nor 5 can be in this list. They're both zero divisors. 1, 3, 4, 5 is out. 6 has got a 2 in it. That's no good. 7, 7's okay. 8, oh, 8's a loser. 9, 9's okay. 10, oh, 10's definitely a loser. 11, 11's okay. 12's got a 2 in it. That's no good. 13, yep, 13. 14, 14's got a 2 in it. It's no bueno. 15 has got a 5 in it. It's forbidden. 16's got a 4 in it. No can-do'sville. 17's okay. 18, it's got a 2 in it. That's out. 19, oh, 19's good. Yeah, there you go. Those are the numbers relatively prime to 20. All right? So what exactly is the structure of the group of units for Zn is actually kind of an interesting and varied answer. It's not the same. There's the pattern, what's going on. It takes a while to really concretely and nicely explain what the structure of Un is. We'll get there eventually. I'm not going to tell you today. What's the order of U20? Looks like 8, right? Now, this order has a name. It's called the Euler-Phi function, or the Euler's totient function. This is phi of 20. So definition, the order of the group of units is defined to be phi n. This is the Euler-Phi function. All right, well, I hope that's enough about that. I should move on here. Before you know it, I'll be out of time. Yes? Just what I wrote. Order of this group is phi n. So, yeah. So it just involves the multiplicative group. You know, the additive group, that's really easy to see, right? It's just 0 to n minus 1, and that's it. And we add. It's the un that actually takes some time to ooh, that red marker. Got problems. All right, let me take a stab at proving that UN is a group. Probably won't do the whole proof. I'll do at least part of it. So what does it take? Theorem. Wow. All right. Yeah. Let's see here. So what do we need to see that that's actually a group? We need what are the things we need? What does it take for this to be a group? We need an operation, right? So I'm arguing that the operation is well defined. I looked at the nuts and bolts of that in prequel 2, where we looked at modular arithmetic. We proved that the product of residue classes is well defined. All right. So I think the first thing I would ask about is closure. All right. In other words, if I have xn and yn both in un, right? Does that imply, question mark, that their product, right? Which, by the way, is equal to what? By definition, xyn is in un. So what do I need? What am I given? So I should assume what? I should assume that the greatest common divisor of x and n is 1, and the greatest common divisor of y and n is 1. What do I want to prove? I want to prove that the greatest common divisor of x, y, and n is also 1. Right? So depending on how much number theory you remember, you may be like, well, we already know that, right? But let's suppose we don't for a second, and let's try to prove it using Bazau's theorem. So what does this theorem say here? It says there exists what? Let's say A, B, C, and D. Haven't used those letters yet, right? Integers such that what? AX plus BN equals to 1. And what else? CY plus DN equals to 1. So what I'm looking for is to use this, right? If I could find something of the following pattern: xy times some number, right, plus some other number times n equals to 1. If I could produce such an equation, then we had a corollary in our study of integers, which proved that if such an integer linear combination of x, y, and n exists, then that proves that the GCD of x, y, and n is just 1, right? This is an if and only if thing, right? This is true if and only if there exist integers such that the linear combination is equal to 1, like so. We've proved that. So can you guys tell me, how can I play with these two equations to get that? Okay, I'll buy that. So you got AX equals to 1 minus BN, and cy is equal to 1 minus dn. Oh, and then just multiply those equations? I think we have a winner. Your argument just made babies cry. You monster. All right. Let's see here. Thought you were in a position of power. Aren't you like a math president or something? Wait, who is the... Oh, you're the president. Are you the vice president, or are you the emperor, the viceroy? I mean, what was your position? Emperor? Okay. Let's see here. Oh, yeah. Then it's just a... I mean, goodness. The math. Plus, I got to add terms, right? I get plus a bn, plus a dn, and plus a bdn squared, minus bdn squared, rather, equals to what? Equals to 1, right? So then you can take this, factor out the n. You got b plus d minus bdn. And that's precisely the number and the number tilde that we so desired. Oh, sorry. Oh, man, now I'm going to have to use the juice again. I mean, I love this red marker, but it comes at a price. There you go. That proves that UN is closed. Because we've just proved that the greatest common divisor of xy is also, with n is also 1, which proves that the product of x sub n and y sub n is, in fact, also a unit. And I'll leave the rest of the proof to your reading, okay? I just thought we should go through at least one part of it, and this, I think, is a good part. So, that is a big, big new set of examples, which is much more divorced from your everyday thinking than the ones I threw out last class, right? Okay, fine. Permutations are a weird example, right? I don't think you would think much about permutations in a previous math class, am I right? But certainly real numbers, complex numbers, rational numbers, integers, these things you were thinking about, you know? Modular integers, maybe not as much. So that's an important new example. We're going to learn a lot about that this semester as we go on. All right. So that brings us to matrix groups. And so I need to describe some general backdrop for you here, which is that if R is a commutative ring, all right, so for us that means it has an identity. In other words, it has a number which, an element in R which serves as 1. Then we can define matrices over such rings. Then I would usually call it Rn by n. Some other people might call it mat n comma r. The point is, it's the set of n by n matrices with entries from these rings. Okay? That itself has a well-defined notion of addition and multiplication. All right, here's the definition. If A and B are in, let's say, Rn by n, and if C is a ring element, then A plus B ij is equal to, and Ca ij is equal to. You tell me what I should put on the right-hand side of this definition. We should not be surprised by this. We define addition by just adding entries, all right? And we define, this is scalar multiplication, so we just do Caij. Actually, that's, I don't know actually if we have too much use of that right now, but it's there, okay? So there's scalar multiplication by ring scalars, just the same. But what's the more interesting thing that gives you guys a little bit more fits in linear algebra? What is it? Multiplication of matrices, right? So A, B, I, J, how is that defined? This is defined as the sum, k equals 1 to n, of aik bkj. Like that. So in other words, all I'm telling you is you can define addition and multiplication of matrices with entries in a commutative ring in the same way you define addition, multiplication of real or complex matrices. Right? And they have all the same properties, the same distributive properties. They don't commute. There's an identity matrix. What's the identity matrix look like? Like you could say I2 is this one, right? I3, what would that be? This guy, right? Generically speaking, IN, the ijth component of it is Kronecker delta ij, which means that it's 1 if I is equal to j and it's 0 elsewise. I mean, otherwise. All right, with all that, we can also define determinant. The determinant of such a matrix is equal to the sum over all permutations of the sign of the permutation times A1 sigma of 1, A2 sigma of 2, dot AN sigma of n. There you go. That's a stone cold formula for the determinant as a sum over the permutation group. If you took my linear algebra, I defined the determinant in terms of a sum over indices. That's equivalent to this. The sign of the permutation is what? It's whether it's 1 if it's an even permutation, and it's minus 1 if it's an odd permutation. So that formula reproduces the plus minuses that you've been taught about determinants in your other class. All right? My point to you, all of these things are available for matrices over a ring. Which means that definition I shared with you last time, right? The definition I shared with you last time for GLNR generalizes. So in fact, definition, G, L, N. See, it's unfortunate I've used R. So let me point out to you the very big difference between this R and the last R. Right? So last class I had R. That's the real numbers, all right? This time I'm putting a commutative ring there. And here's the definition. It is A in Rn by n such that the determinant of A is an element of the units of R. So here, U of R is equal to R in R such that R is a unit. You can prove that in a ring, if you take the set of all units, the set of all things with multiplicative inverses, that forms a group. All right. Now, to prove that that's a group, you should prove various things, right? Number one, that the multiplication is closed, right? So is the product of, well, actually, I'd rather not get into the proof of why that's a group at the moment. I think to do that properly, we also need to have proved that U of R was a group. And I'm sure I addressed that in a later lecture, so I should probably focus on specific examples for today. That was really the purpose of this, is not so much to prove that this is general and true, it's to give us more examples. Let me get to the more examples. So here's some examples. I should say this much. The formula for matrix inverse that comes from dividing by the determinant and looking at what's called the adjugate or the classical adjoint, that formula still makes sense over a commutative ring. So as long as the determinant is a unit, the formula that you learn in linear algebra for the inverse still makes sense. So that's why that condition suffices to, that condition implies that A is an invertible matrix over the ring is what it does. All right, so let's look at something a little bit more concrete here. How about GL2 Z3? What would this be? This would be things like A, B, C, D, right? In Z3, 2 by 2, such that what? We need that the determinant is where? The determinant of AD minus BC. I should mention, we did have at least part of a proof that U of Zn is a group in here today, right? I'm just saying I haven't proved it for an arbitrary ring, and maybe we should wait to do that until we have a discussion about arbitrary rings, okay? That's all I'm saying. I'll stop saying these things. And this has to be an element of what? The determinant of AD minus BC in where? According to my definition. U what? U of what? Of Z3, which we called what? U3, right? Which, oh, check it out, just like I planned. Which happens to be this. All right? Just as I have planned. So anyway, long story short, the determinant has to be either 1 or 2. That's kind of a quirky thing. In fact, it just amounts to the non-zero determinant in this case. So, I mean, how many matrices are there in Z3 2 by 2? What is it?
For the second half,
Oh,
not the determinant, right?
yeah. Thank you. Sorry. Thinking and writing, hard to do at the same time. And while we're at it, well, anyway, at some point there needs to be a close of the set, but here's a matrix. 1, 3, 7, 0, fine, 7, 2. What's that equal to? What is that in Z3 if we're writing it in terms of, not weird representatives of Z3? I would trade that 1 for a 1, that's fine. 3 is more commonly known as 0 in Z3, right? 7 is 1. And what's 2? 2, all right. Is that an invertible matrix in Z3? Well, its determinant's 2. So, yes, it's invertible. What is its inverse? Ah, glad you asked. So, 1, 0, 1, 2 inverse is equal to 1 over 2 minus 0. You flip the diagonals, and you put minuses on the off diagonal. So that's what? Now, what does this mean? So I don't usually write this, guys. This requires some interpretation, doesn't it? What does that actually, what do I actually mean by that? So let me put it in different terms. What should I have written there? And what should I write for the inverse of a matrix with entries from Zn? 2 by 2, 2 by 2. So here's a general formula. A, B, C, D, inverse. It's AD minus BC, inverse, times the matrix. We flip the diagonals, and we put minuses on the off diagonal, like that. So that formula, properly interpreted, still makes sense for matrices with entries in a ring. So what do I mean by, so let's see here, let's try that out. 1, 0, 1, 2 inverse should actually be what? It should actually be 2 inverse, right? And let's get rid of the minus. What is minus 1 mod 3? 2, right? What's the inverse of 2? What's 2 inverse mod 3? I unfortunately just erased the Cayley table that would have told us the answer. 2 is its own inverse, right? Because 2 times 2. So 2 inverse is equal to 2. Now, if you want to annoy certain professors, write it this way. Right? don't recommend it. It won't annoy me much unless you use it without understanding, in which case I'll be annoyed. But it's okay. I'm annoyed most of the time these days. So 2, 0, 2, 1. So that gives me 4, 0, 4, 2, also known as 1, 0, 1, 2. What? Is that what we started with? Check it out. This matrix is its own inverse, right? That's a funny thing. So what we just proved is that A inverse is equal to A as it happens, right? What's the order of this matrix as an element of this group, GL2Z3? If an element is its own inverse, what's its order? This says what? A times A equals to the identity, right? So the order of A is equal to 2. What's the order of GL2Z3? What's that? Let me start with an easier question. If we look at just Z 3 by 3 paired with addition. Oh, not 3 by 3. Goodness. What I wanted, that's an infinite group, the one I just wrote. Here we go. So entries from Z3, 2 by 2 matrices. For example, you might have this one, 1, 2, 0, 0. Call that M. There's a matrix in there. What's its order? M plus M is what? 2, 4, 0, 0. Also known as what? 2, 1, 0, 0. What's M plus M plus M? We get 2 plus 1 is 3. We get 3, 0, 0. We get 0. So therefore, the order of M is 3. That's an additive order. That was a multiplicative order on the one we just did. Now I can answer the question, what's the order of this group? See, the set of 2 by 2 matrices with entries from Z3 is an additive group. What's its order? That's not a hard question because you just have to count how many matrices can you make that have got 4 entries, and each one of those entries can take 3 arbitrary values. 3 to the 4th, right? 81 such matrices. How many of those 81 matrices are invertible? I don't know. I'd have to stop and think about that. So we found a matrix which was in here. What is the set of all such matrices? Well, that's kind of complicated. All right. Now, one of the interesting examples in the notes right here is given to us. I think one example that's kind of surprising is if we look at what was the quintessential ring? What did I tell you guys? So if we look at GLNZ, this would be A in Zn by n, such that the determinant of A is equal to what? What are the numbers? I can just write it in terms of case-wise equality here, because there are only 2 units in the integers. What are they? We talked about this last time. 1 and minus 1. So this thing is just the set of matrices which have determinant plus or minus 1. And I show even for 2 by 2 matrices, there's infinitely many such matrices. That's example 2.2.18. The other interesting example, and I'll stop with this, is that if you calculate GL2, Z2, you can show that you have the following matrices. 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, and finally 1, 0, 1, 1. How many matrices are there in there? There are 6. And if you calculate these matrices, and if you study them and study their order, this is the identity matrix. I believe this one squares to the identity matrix. I might have a typo in here. I don't know. Like three of these matrices have order 2, and 2 of them have order 3, right? What I'm trying to tell you is if you study the order of the matrices here, you'll find out it matches precisely the orders that we saw for the cycles in S3 earlier, right? So this, again, leads me to the next class, which is I could make a comment that group of 2 by 2 matrices is actually just another way of looking at permutations on 3 elements. In fact, that group is isomorphic to S3, as we'll try to describe carefully next class. So anyway, our world just got a lot bigger, but I hope it wasn't too confusing. Thanks, guys.